But before I'd start, I just want to indulge myself with a bit of audience participation. So I'm going to ask for a show of hands. But don't worry, it's not about Brexit. It's actually about a particular thesis of mine. So my question to you is, how many people in the audience play a musical instrument? Okay, that's about 25, optimistically, 25%. And how many play a musical instrument in a band and do concerts on a regular basis? 2, you and me. I'll see you afterwards. Okay, when I worked at Philips about 1 million years ago with Liam, who's around somewhere still, about 50% of the group were musical or of some kind. So it's kind of interesting to see the difference today. Okay, nothing to do with millimetre-waves or whatever, but interesting nonetheless. So who is Blu Wireless? I'll start with that first. So we've been around about 10 years. We're based in Bristol. We actually started out as a digital modem company to develop gigabit rate modems for millimetre-wave applications. So the core team, we have about 30 silicon engineers in the team, are focused on developing incredibly complicated baseband modem technology based on our own proprietary processor architecture. But along the way, we figured out the best way of selling it at the best price was actually build products, and not just to build chips. So we actually work with millimetre-wave RF partners to integrate with our modem and then develop cutting-edge products for various applications, like transportation, which Helen mentioned at the outset. So there's a few examples here. So here's a 28 nanometer chip. We heard about 28 nanometer before, but this is a digital chip. This is around 800 million transistors, 17 individual processors, 6 proprietary hybrid hardware-software parallel engines of our own design, and 2 3.5 gigasample AD-DA converters. That's gigasample AD-DA converters. So this thing can process 2 gigahertz channels and generate a data stream of about 6 gigabps from one piece of silicon, which consumes about 2.5 watts. And it was right first time, which was a big surprise to our customer, who was clearly not expecting that. Anyway, as well as building the chip, we then put that into various products with millimetre-wave, and we actually have 2 ongoing application projects. The first one is fixed wireless access, and this is in the city of Liverpool, where we're part of a UK 5G testbed funded by the DCMS, the UK government. And we have a network of about 100 millimetre-wave nodes on lampposts around the borough of Kensington, attached to the Liverpool Hospital. The other project is a 5G testbed at Millbrook. This is not at Millbrook, this is actually on the Top Gear test track at Dunsfold. This is a McLaren sports car. We work with McLaren on various aspects of this. So they wanted to know how fast millimetre-wave would go, and they didn't believe us when we said it would go. It will work rather at many hundreds of kilometers an hour. So they got this guy out of the garage, and I think we did 280 kmph with that down the runway before the guy had to apply the brakes, and no problem with our system. And the final project is this one. This is guess what? It's a train. In case you didn't know, this is actually one of the new Crossrail trains on the Queen Elizabeth line when they finally open it. This is on test at the Network Rail Riddick test facility in Melton Mowbray. And we piggybacked on millimetre-wave. On the track side, there's a couple of our nodes here on the roof of the train. And we went up and down the line for 3 months or so, characterizing the performance of millimetre-wave in a train environment. And this was a preamble to a commercial project that we started earlier this year with the First Group company. First Group is the UK's largest train company. They run the South West Line, they run the Great Western Line, and now they've just won the West Coast franchise as well, from London to Glasgow. So we're putting millimetre-wave on trains for South West Line to start with, and that will improve the on-train Wi-Fi coverage, which I'm sure everybody would agree, if you tried it, it's pretty rubbish at the moment. So that's a leading application for us as we go forward. So I mentioned these 2 projects. Autoair is the Millbrook testbed, and the other one is Liverpool 5G. They're 2 out of the 6 projects. And coincidentally, DCMS think these are the 2 best projects. And of course, I would say that, wouldn't Remember the Wi-Fi Alliance, UK 5GIC, which is the organisation at the University of Surrey. And we're also involved with the Facebook TIP project. And next week in Amsterdam, there's the Facebook TIP Summit. So we'll be there demonstrating our stuff. And of course, we need to spend lots of other people's money to do all this stuff. So we've got ARM and Calculus and many others in our investment pool. Most of our customers are either stateside or Japan. And in fact, First Group is arguably the first, pardon the pun, UK customer that we actually have. All right, so let's talk about spectrum. And this is my Mickey Mouse guide to the millimetre wave spectrum. We've heard about 28 gigahertz so far today, where there's a lot of licensed activity. Some people might know that Verizon spent $3 billion in the United States buying 50% of the US spectrum at 28 gigahertz. A lot of money for fresh air. 39 gigahertz is another licensed frequency, the US side. I think in Europe it extends down somewhat lower than that into 26 and below. The one that's interesting to us is unlicensed millimetre wave. We like unlicensed, and so do our customers, because it costs nothing. And there's no better number than 0 as far as the customer is concerned when it talks about a cost. Recently, the CEPT changed the rules to be more in line with the US FCC rules for operation between 57 to 71 gigahertz. So that's 14 gigahertz of free bandwidth with 10 watts of EIRP. You can do a hell of a lot with that from the point of view of a radio engineering product company. And this is being adopted through European law, through Directive 1345 from the 1st of January 2020. And I have to thank Ofcom. Ofcom were the chair of that committee at CPT, and they were very instrumental in helping push that forward. And this allows, well, I've said here 6 by 2 gigahertz. You've got 14 gigahertz to play with, so you can move anywhere you want across that band with that 40 dBmi. And in fact, the CPT rules allow you to go to 55. On the proviso, you've got 30 dBi of gain. So you can go even higher than that if you have a high gain antenna. Okay, here's my beamforming slide. Lots of people have beamforming slides this morning. So here's mine. So on the transmit side, you start with a single input. You split it n ways. You phase shift it to steer the beam. You perhaps attenuate it to put some attenuation profile across the aperture. You then have an amplifier per chain. As mentioned, generating Barrett millimetre wave is challenging from a semiconductor perspective. Typically around 10 milliwatts plus or minus a bit is the KPI for that. And then you put that into an array antenna, and then you've got this coherent wavefront, and you steer that across the face of the array. And you reverse the process in the receive side. In this case, you've got low-noise amplifiers feeding a receive chain. You combine it, then you down convert it to baseband, and then we do our modem magic to generate the gigabit data stream. So on the power budget side, on the TX, you get an n squared gain, n being the number of elements. You get coherent addition from the PAs and coherent addition from the antenna elements. On the receive side, you only win once because noise goes up as well as power. Noise goes up by n, power goes up by n squared, you get an n gain on the receive side. So 20 log on TX and 10 log on RX. The other interesting point to make is that for a constant aperture, gain goes up by a factor of f squared with frequency. So across 57 to 71, you get 1.9 dBs for free if you set your aperture for 57. So that's interesting from a link budget perspective. So one of our partners is a Swedish company, Sivers IMA. Many of you have heard of them. They've been around since the 1950s. With various microwave components. These days, they're making advanced RF SoCs. This particular device they call EDA. It's a SIGI by CMOS single chip millimetre wave device which integrates 16 receivers, 16 transmitters, beamforming networks with around 5 bits of phase shift and amplitude control into an IQ up and down conversion. It's a direct conversion architecture. Tunes across 57 to 71 gigahertz. Excellent phase noise. We can do 64 crime or even better from the phase noise it can deliver. When we combine that with this simple phased array antenna, where we've got 16 columns for TX and 16 for RX, each is a 4-element patch combined to a passive array. We get about 23 dBi from that guy. Put it together, we can exceed the limit of 40 dBmi and get up to 43 dBmi. to show some beams in action. These are the 6 channels which are defined by the 11AD spec that we generally use in most of the stuff we've been doing. We can work around these channels, but anyway, these are the 6 2 gigahertz channels, and you can see the 40 dB MLIs here, and the beam is steered plus or minus 45 degrees, a bit more than azimuth, and there's around 64 beams across that aperture. Each beam is about 8 degrees in beam width, so we get multiple beams per beam width, so we get a pretty good close overlap. So it's a very useful, very powerful radio. And in the protocol, what we do is we use the Beambook to actually do a scan, so we acquire the TX and RX beams dynamically as the TX is looking for the RX and vice versa. So it's a Beambook-based approach. It's pretty common in most of the phased array solutions you hear about in the marketplace, including 5G new radio from the 3GPP. Okay, so what? On the baseband side, what's the big deal? What's the problem? Well, the problem is we've got a 3.5 gigahertz sampled front end throwing this deluge of data at this modem. It's got to turn that into useful packets and bits that can be connected to an internet connection or whatever. Unlike most wireless systems where the sample speed is much lower than the clock speed of the processor, the opposite is true here. So we need a lot of parallelism to keep up with this 3.5 gigahertz front end. In fact, we need about 8x parallelism to cope with an SoC clock speed on my 28 nanometer chip of about 500 megahertz. So we've designed a parallel processor DSP engine that can do that, and can do that with software-defined capability. So we can fiddle around with equalization, we can fiddle around with modulation, demodulation, and do a lot more tricks besides. So there's a whole menu of items that we have to process in real time, in a nanosecond time frame, and then successfully capture, decode, demodulate, and present those packets to the MAC layer. And then the MAC layer has to keep up with around 1 million or more packets per second, encryption, decryption, point-to-multipoint control, beamforming control, and synchronization, for example, for a small cell. A lot going on very quickly. And all that requires around a tera-op of DSP. You want to do that without burning a hole in the planet with a whole array of FPGAs, as you see in most LTE base stations, which seem to be more about boiling water than they are about generating bits. But nonetheless, without putting it onto an SoC, we'd have the same problem. So here we've got effectively 2 terabytes. So you've got 2 modems and 1 chip within a 2.5 watt envelope. So this is on our Hydra 1 technology, which is 11AD with extensions for infrastructure outdoor applications. Each physical layer can go up to 7.5 gigabps with 64 QAM. We've got a bunch of stuff in there to cope with co-channel interference, RF phase noise mitigation, and a long list besides of all the different things. We're working on the next gen, which is 11AY. That takes it up to 34 gigabits, so that includes channel bonding, channel aggregation, and MIMO. There is some ability to do millimetre-wave by using some reflections, but that's coming soon. So we design the architecture. We spend a lot of time with our 30 or so silicon engineers. We turn it into this lump of 28 nanometer. We then put it into metal boxes with phased array antennas and GPS. In case somebody nicks it, we need to know where it's gone. So that's an important function. So baseband modem. The other thing we do is we like to license our technology to companies who are much bigger than we are. So IDT, which is now part of Renesas, took a license from our technology, and we did a turnkey chip design for them. So this device is actually available for purchase from IDT. It's been in mass production since last year. I can say 2 modems, IQ in and out, physical layer, MAC layer. We combine the 2 streams, we put it through PCI Express and connect that to a network processor for the applications. Radio-wise, we started with Cybeam. Cybeam was a famous company, very much a pioneer in millimetre-wave on CMOS. Then we've moved to the Sivazima device, which I've already described. And we're doing some work with Nokia Bell Labs on their 90 gigahertz radio. And for those radio heads in the audience, if you want to look at that chip, it's a fantastic piece of work. There's a JSSC paper, which was published in August of last year, which describes that chip. It's worth a read on its own. So, yeah, okay, and the rest I've already said, I think. Of course, it's heavily software-defined, so we've got a very sophisticated Linux framework and a driver that talks to the chip and sets it up with all its various modes. Then we put it in the metal box. We call it Metalbox Typhoon. We support all the features, and we have an API which allows our customers to go in there and play. And every time I present this to customers who are interested, I usually come away with a purchase order. So it's a very interesting box for many reasons. And one of the key KPIs is that this entire box only takes 40 watts. 40 watts for a box that can do 3 gigabits. That's extremely power efficient at these phases. And by the way, of that 40 watts, 30 watts is the Linux computer. The radio and the modem is less than 10 watts. All right, so the other thing is, what is the data rate, and isn't 60 gigahertz a waste of time because of oxygen absorption? Well, okay, it is. If you look at the plot of dBs per kilometer versus frequency, you see this famous peak, which is 60 gigahertz for oxygen absorption, somewhere around 15, even to 20 dBs per kilometer. But as soon as you get above 65, virtually nothing. So you're into very low loss there. So one of the first things we did was to go find a long stretch of beach and do some measurements earlier this year with the new Civers radio integration. And you can see on the left-hand side, channel 2, which is down at 60 gigahertz, you've got the 15 dB per kilometer overhead. We're getting about 300 meters at 2 gigabps. As we go out to channel number 6, which is right at the other end of the band, around 69 gigahertz, you can see that that range has effectively doubled. And since then, we've improved the performance of the front end with various methods, and we're now over a kilometer at the top end of the band. So millimeter wave is not short range. We can shoot gigabits over half a kilometer or more. Okay, onto the Millbrook thing, which is what was exciting Helen at the outset. So this is the high-speed test track at Millbrook. This is about 30 miles from here. This is a 2-mile circumference 4-lane highway, which is a banked highway. It was built by General Motors in the 1970s for testing Vauxhall motor cars and trucks, but it's now a privately held facility. And this is a consortium of companies working on this Autoair 5G testbed DCMS-funded project. And our piece of the project is to deliver this millimeter wave testbed. So we've got a network of 11 towers around the circumference of this bowl. Each tower has a radio looking backwards and forwards. And then what we do is we put a dual radio on top of the vehicle. We call it a TN. It's called a train node for reasons that will come apparent later. Then we look up and down the track, and as the car goes around the track, it makes and breaks association with each of the towers to generate a continuous connection all the way around. And then all the towers are fiber optic connected together at layer 2 through a switch into a gateway, then off to the internet. So it's a very convenient way of tracking data, and we can sit in Bristol and control this thing and monitor the data in real time as the car whizzes around the track. Phase 1, we started at 60 gigahertz with the aforementioned Cybeam radio, and that was a bit limited in performance, but we've doubled that now with the new 5771 gigahertz radio, and it's really looking extremely exciting in terms of the performance it gives. And here's some nice photographs. This is the Typhoon silver box. The radio is behind the plate here. There's a GPS. I don't think there's any fear of being pinched at Millbrook, but anyway, it's there. We've got, you can see the 4-lane highway. The bank is such that you can do 130 miles an hour at the top end of the bank, and sometimes faster than that if you've got the right car. The one in the middle is the car-mounted unit. In fact, this is a prototype for the train-mounted unit I'll show you later. Radio front and back again, and that's a side view, of course. Then, of course, you need some cars to make this all hang together. So here's some photographs from some customer meetings that we had at Millbrook to show people the capability. So this is a McLaren 570S. This is a Honda Civic R. In fact, this is the first Honda Civic R built at Swindon. So it's an extremely fast piece of equipment, arguably almost as fast as the McLaren. And then this is a high car Mercedes, much more space inside a Mercedes, so we can take customers around in comfort. So they're the three cars used. And again, you can see the TM mounted on the roof. Inside the car is the Linux processor, which happens to be ARM-based. So then some results. The other thing I mentioned was McLaren. So if you watch Formula One, you'll see all the squiggly lines that are on the curves as the cars go around the track. That's generated by a tool they call Atlas. We have Atlas embedded inside our system as well. And what we do is we record all the key KPIs from the modem, we export that to the server, and then we can display that in real time to see what's going on with the modem and the system. So Here we're showing the modulation coding scheme. The higher the better, so typically 0 to 12. 12 is 16 QAM, 0 is 27 megabits, 16 QAM is around 4 gigabits physical layer, 3 gigabits at the data layer. Then we show signal to noise. This is amazing. We're seeing signal to noise in the region of 20, 18 dBs. Normally we're scrabbling around in the 5, 6, 7, 8 dB region. So it shows that these radios really are much more powerful than the previous generation. And then finally we have throughput. We have front and back radios, and we also overlay with speed, 130, 170, 190 kmph. This staircase is association for each of the 11 towers, so that's basically one lap around Millbrook. So the net of all this is that we're seeing a 1.6 gigabps average speed and a 3.1 gigabit peak. And what's really interesting is the latency. The latency is unbelievable, 0.7 to 0.9 milliseconds. And that's through a gateway, which is a McLaren product on the car and on the track side, and over the millimeter wave. The 5G guys, the 5G new radio guys, I should say, are talking about 2 milliseconds as the magic number, and they're struggling to meet that. We're already less than half that with this solution. We haven't even bothered optimizing it yet. So this is extremely low latency system. And as a comparison, we also have a private 4G stroke 5G network, I should say, at Millbrook, which is also part of the same Autoair project. Typically, they see 40 to 60 milliseconds latency and peaking around 300 when they have to do some difficult handover. So this is an extremely low latency system, and that in itself is an interesting consideration for applications. Okay, so picture of a train. Okay, it's a Japanese train. Japan is an interesting country for this, but I think it's also interesting in the UK, and working here with First Group as our partner. We're going to market with First Group and using their contacts to generate business with various train companies around the world. The first question is, why bother? Well, the reason to why bother is twofold. Number one, what they do at the moment is they take LTE off the roof of the train through 4 SIMs, they aggregate that and feed that through the Wi-Fi access points in the train. Problem is that the LTE coverage along train tracks is not great, and also the moving village of passengers on the train generates a super chunk of demand, which is really difficult to manage as the train crosses through cell boundaries. So it's a difficult cellular problem anyway. And the second why bother is the cost. The average cost of wholesale data is around $3 per gigabyte. And if you do that sum, assuming that each train is consuming about a gigabit of traffic, it's an enormous amount of money. And therefore, if a train company wants to support that kind of demand, the economics show you that it's much more economic to deploy your own dedicated trackside network than it is to keep buying the data from the operators. So that's another very important consideration. And where is this demand coming from? Well, if you go to Ofcom's website, they did a report last year to the UK government on estimating the demand, and they came up with demand curves which were at least a gigabit and going north of that as trains go into ever higher capacity. Deutsche Bahn did the same thing in Germany, and they came up with pretty much the same numbers. So the demand is there, and the economics point to a different solution other than just using 4G or even 5G. 5G NR at 6 gigahertz, 3 gigahertz, I should say, will give you about 200 megabits. And what Deutsche Bahn said was if you pointed the entire capacity of the German 5G NR network at the trains, you'd only service 30% of their demand. So clearly that's not going to happen, but that's a limiting case. Okay, so what we're doing is we're putting trackside towers roughly every kilometre if we have a straight line, and we're putting radios front and back of the train. Each radio is a dual radio, and that's on a 200-metre length, can be anyway on some longer trains. Then there's an on-train backbone, an Ethernet backbone, which we use to aggregate the data and feed that through Wi-Fi access points in the carriages. And then the trackside network has a dedicated 10 gigabit layer 2 network, which then connects through a layer 3 switch onto the external internet. And here you see a couple of photographs. This is the TN unit, which sits on the roof at the front and back. The most expensive component in the entire product is that chunk of aluminium, which is there to short circuit the overhead line when it falls on top of the train, rather than short circuit the passengers inside the train. That's a pretty important safety consideration for the system. And the guy over here is the trackside unit. These are mounted on the poles. They have 2 radios looking up and down the track, and the rest of the electronics is the modem and the network processor to control the system. So we're in the midst of developing these products. They're going through radio type approval now. We'll be deploying them in Q1 of next year on South West Rail. Here's some more holiday snaps. These are from the Network Rail Riddick trial from last year. You can see the TN unit here. It's mounted on a riser to clear the HVAC unit, which is in the front of the train. There it is again. And then there's some shots of what's happening on the track side. Here's a couple of units mounted on the overhead line stanchion. There's 25,000 watt cables here. And there's a dedicated tower that we designed and put up at another point in the network. One more point to add, the system also can switch between existing Wi-Fi and 4G services using the on-chain aggregation unit. Because the train company isn't going to put this everywhere, it's going to put it where the demand is, at least to start with. So the system has to switch backwards and forwards between the existing 4G-based system and the millimetre-wave system. This is a map of the South West Rail network. We're in the middle of doing some proving trials on the Isle of Wight at the moment. The deployment will be between just south of Clapham Junction all the way down to Basingstoke. That's about 70 kilometres. And we're going to put that around 200 trains that go up and down that line as the first step. And that meets the criteria set by South West Rail in their franchise agreement with the UK government. Okay, so that's the end. So some takeaways. So phased array radios at 5771 gigahertz are here today. They're commercial elements. You can buy them from partners such as Civizeme in our case. They work extremely well. They deliver carrier-grade performance. By combining that with some of the features of our modem, we can really deliver some very interesting infrastructure-style applications. We can meet and exceed the 5G KPIs as set by the ITU at the beginning of the 5G story. More than a gigabit and less than a millisecond latency for road and rail applications. We're talking to road application companies as well, particularly in Japan, who really are interested in using this band for V2X applications. The 5G testbed at Millbrook has already validated many of the KPIs I've been talking about in this presentation, and we're deploying this commercially starting in the UK from the beginning of next year. Okay, thank you very much, and there's a picture of a train.